We said that, let me turn this little light on. Last Wednesday, we said that we would start here on Monday. And I want to go back just a bit and look at how you find the components. So if you have a vector PR and P is 2, -5, R is -6, 1. And you want to write PR in component form. So first, it helps to see where you are. So 2, -5. And R -6, 1. So we're going from P to R, and we're going to go 8 units to the left and 5 plus 1, so 6 units. That means that's exactly what I need to do. Oh no, I don't even have to do that. All I need to do is take P and send it up there. So let's see. I need to subtract 2 and add 5. So let's see. If we take R and we subtract 2, that'll give us -8. And we add 5, that'll give us 6. Then that will be the component. So then we would say that PR is equivalent to -8, 6. And the component form is just super handy. Hi, Krista. So if vector U is U sub X, U sub Y, and vector V is V sub X, V sub Y, vector W is W sub X, W sub Y, and C and D are scalars. So they're just numbers, they're not vectors. Then we have these properties. The definition of addition is we'll take the X components and add them, and the Y components and add them. And this is called component-wise vector addition. It is commutative, which means it doesn't matter what order you add them in. It is associative, which means it doesn't matter how you group, whether you add U and V first or add V and W first, you'll still get the same result. There's a zero vector. If you add u to the zero vector, you get u back, and u plus negative u gives you the zero vector. So before we look at some of the scalar multiplication properties, let's look at property 5. So we have u is u sub x, u sub y, and we know that, we know that the zero vector is just 0, 0. And we want to see, is it really true that if you add the zero vector to u, any u, you'll get that vector back? So we've got u plus 0. And so first we're just going to replace each with their components. So u is u sub x, u sub y. Zero is 0, 0. And to add, we already said that to add, we just combine the components. So u sub x plus 0, u sub y plus 0. And u sub x plus 0 is u sub x, because this is just number addition. U sub y plus 0 is just u sub y. And this is exactly u. And let's look at one of the properties that is, let's look at the commutative property. So we've got u is u sub x, u sub y. V is v sub x, v sub y. And we're going to begin with u plus v. So we already said what addition looks like. We're going to add the components. So u sub x plus v sub x, u sub y plus v sub y. But now this is regular number addition. We're not looking at vectors anymore. And I know that with numbers, with real numbers, I can switch the order. So I've got v sub x plus u sub x. And the same here, v sub y plus u sub y. And now I can see that this is exactly v plus u. So I just wanted you to see that these properties are not difficult to prove. Next, let's look at scalar multiplication. And what we mean by that is, say if we have a number 5 and we have a vector 2, -1, then, and this would be C, then we would have C times U, and we're defining that to be 5 times 2, 5 times -1. So we just multiply the scalar through. If we have the sum of two vectors and we've got a scalar outside, we would multiply it by everything so the distributive property holds. We also have a distributive property if we've got two scalars and one vector. So we would multiply the vector through. So CU plus DU. We have an associative property. So CD times U is C times DU. We have an identity. If we multiply 1 by U, we get U back. We have a 0. If we multiply the number 0 by the vector U, we get the vector 0. And if we multiply any number by the vector 0, we get the vector 0. If we look at the modulus or the magnitude, the product C times U will give us the absolute value of C times the modulus or the magnitude of U. And let's see, let's look at 12 and then 14. So 12 is a 0 property. We've got 0 times U. So we know that 0 is just a number. It's the number in the real numbers. And that U is U sub X, U sub Y. And we defined scalar multiplication as multiplying this scalar through the components of the vector. So let's see, this will be U sub X, comma, U sub Y, and then we'll multiply 0 times U sub X, 0 times U sub Y. And now we're looking at numbers here. 0 times U sub X is 0. 0 times U sub Y is also 0. And this is the definition of the 0 vector, which is what we were trying to prove. So the number 0 and the vector 0 are not the same. They're related, but they're not the same item. Let's look at property 14. And that's the one where we've got a scalar times a vector, and we're looking at the magnitude of it. And we want to show that this is the equivalent to the absolute value of the scalar times the magnitude of the vector. So we've got C times U And we know that this is C times u sub x times u sub y. And let's go ahead and multiply. This is C u sub x, C u sub y. And we know that the magnitude is the square root of the x and y components squared. So let's see, this will be C u sub x squared and C u sub y squared. And that is C squared u sub x squared plus C squared u sub y squared. And I've got a C squared common, so I'm going to factor it forward. So I've got C squared times u sub x squared plus u sub y squared. And now I've got the product of two things, so I can split this up. So I've got the square root of C squared and the square root of u sub x squared plus u sub y squared. Well, this second root is exactly the magnitude of the vector u. And if we square any number and take its square root, whether the number was positive or negative, we'll end up with the positive. So what's important is that a scalar times a vector will not change the magnitude of the vector, but the scalar itself remains a scalar. Its absolute value actually comes out to be absolute value. We said that vector addition was, if we did it component-wise, it was u sub x plus v sub x, u sub y plus v sub y. But there's a geometric way. In fact, there are two geometric ways to add vectors. So there's a way called tip to tail. So I'm going to draw vector u and vector v from the head of u, and then from the origin, I'm going to go out to the head of v, and that will be u plus v. There's also a parallelogram method. I put both u and v in standard position with their tails at the origin. And then I complete the parallelogram. From the head of v, I put u. From the head of u, I put v. And then from the origin to the farthest corner will be u plus v. And you can see that it doesn't matter which geometric method you use, you'll get the same. So let's find u plus v. Let's see, we've got u is 4, -3. and V is negative 2, 5. And we want to find U plus V geometrically and component-wise. So component-wise, we have 4 plus negative 2 and negative 3 plus 5. 4 plus negative 2 is 2. Negative 3 plus 5 is 2. So we can see that the sum should be 2, 2. So let's see. All right. So we've got U. U is 4, negative 3. V is negative 2, 5. And we're doing the parallelogram method first. So from the head of U, I want to draw V. So V was negative 2, 5. So I go back 2 and up 5. 2, back 2. And I do the same thing from the head of V. I draw U. So U was 4, negative 3. So I go to the right 4 and down 3. So see, we're at negative 2. Go to 2 and I go down 3. And the sum is from the origin to the other corner. And you can see that we get the same value. And let's do the tip to tail method. So U was negative 4 and negative 3. So we know that U is 4, negative 3, and V is negative 2, 5. So I go back to the left 2 and up 5. So let's see. From 4, we go back to 2, and we go up 5. So we go up to 2. That is V, and the sum starts at the origin and goes to the edge. And you can see that we're doing the same thing on the parallelogram method when we complete the box, when we complete the parallelogram. So we still have this UV corner. All right. Unit vectors. A unit vector has a magnitude of 1, and it usually is written with a caret. What do we call this also? I can't think what else we call this, but this little hat is called a caret. To find a unit vector in the direction of a vector u, we want to take the vector u and divide it by its magnitude. So let's see what that would mean. We've got the vector u and the magnitude and I know the magnitude is a scalar, so this is the same as the square root of u sub x squared plus u sub y squared multiplied by the vector u sub x, u sub y. So what I'm doing component-wise is I'm multiplying u sub x by the reciprocal of the magnitude. And I'm multiplying u sub y by the reciprocal of the magnitude. And let's notice that this new creature, let's find its magnitude and let's call it u caret. So its magnitude it'll be the square root of, we'll have u sub x squared, and we'll square the square root. That'll give us u sub x squared plus u sub y squared plus, we'll square the y component, so we'll have u sub y squared and we've got the square root squared, so we're just going to have the element under the root. So we've got u sub x squared plus u sub y squared. That's a u. And now we've got a common denominator, so we can add. In the numerator, we're going to have u sub x squared plus u sub y squared. In the denominator, we're going to have u sub x squared plus u sub y squared. And that is 1. Everything in the numerator matches everything in the denominator. So we have the square root of 1, which is 1. So to create a unit vector from any vector, we can divide by the magnitude. So let's find the magnitude. Oh, pardon me. Let's find a unit vector in the direction of u, where u is 5, -2. So we need to find the magnitude of u. So 25 plus 4 is the square root of 29. And that means that the unit vector in the direction of u will be 5 divided by the square root of 29, -2 divided by the square root of 29. In 2 dimensions, the most common unit vectors are I and j. I is in the direction of the x-axis. J is in the direction of the y-axis. And if we were in 3 dimensions, we would have k, which is in the direction of the z-axis. So any vector can be written, if I have u, instead of writing u sub x, u sub y, I can write u sub x, the scalar, times I, plus the scalar u sub y times j. And we can draw I and j there's I. It's 1 unit long and it's along the x-axis. And j is 1 unit long along the y-axis. So in other words, if we've got a vector, let's say we have the vector 5, -2. I can write that in with unit vectors as 5i plus -2j. And now, if I graph this, all right, so if I want to look at u, this is saying that I can do 5 times this unit vector. So 1, 2, 3, 4, 5. -2 times this unit vector. and the result is vector u. So we can take any vector and represent it with its x and y components two different ways. We can do it what we call component wise, where we have angles with 5, -2 in between, or we can write it without any notation as 5 times I caret plus -2 times j caret. So for any vector, yeah, to write it in component form, we put it in standard position. So if P is 3, -1, and R is -1, 2, then we can, let's see, we're going. So there's P. There's R. So to make this in component form, I need to move the head of P to the origin. So I need to go back 3 and up 1. So I'll have R will go back to -1 -3 and up 1. So 2, let's see, that is -4 and up 3. See that that's the same. Just position. The PR in component form would be -4, 3. Given a vector component form, magnitude, the direction, magnitude is going to be v squared plus v sub y squared, the square root of thing. And the direction is going to be the arctangent of v sub x. We'll have, and we must make sure that theta ends in the same quadrant as the vector v. So let's do example. we'll get the magnitude direction. So using images, we've got vector V, and it has a magnitude of V. And we're finding its component by sine and cosine. But that's what we're about to do. So let's see. If we have V in component V is 2I minus J. The magnitude of vector V is 2 squared plus negative 2 squared. So it's square root of 2. And we know that theta is the arc over x negative 2 over 2 negative arc negative 1 negative, and that'll be negative pi. So we know we've got a picture. In which quadrant was V? He was in the quadrant, so that's great. So, but we usually express the angle as a positive. The angle in the fourth quadrant with the denominator is, so we're going to let theta is 2 square root of 2. Would V is equal to, and this is like the R cosine theta thing. So it would be equal to 2 square root of 2, the cosine of 7 pi over 4, sine of 7 pi. If we started with the magnitude and the angle, then we're going to have the situation where we're going to find the two directions. So if we've got an angle of 2 pi over 3 and a magnitude of 3 square root of 2, and this is 2 pi over 3, we want to find the x component and the y component. So to find the x component, we know that this is theta, so we're going to multiply. We know that the sine of theta is going to be, this is v sub x over here, v sub y, so it's going to be v sub y over, and this is the magnitude, And I want to find v sub y. So I'm going to multiply both sides by the magnitude. And we'll do the same thing to find the x component. We know that the cosine of theta is v sub x over the magnitude. And we can multiply both sides by the magnitude. So the magnitude times the cosine of theta will give us v sub x. So in our example, we've got the angle is 2 pi over 3. And I'm just going to write down really quickly. This is a pi over 3 angle. So I know that at pi over 3, I've got a cosine of 1/2 and a sine of square root of 3 over 2. So in quadrant 2, the cosine will be negative and the sine will stay. All right, that helps. So now I've got v sub x. Well, the component, the magnitude of the vector is 2 square root of 2. Is that right? Seems weird. Oh, 3 square root of 2. And the cosine of theta, we just said, was negative 1/2. So we get negative 3 square root of 2 over 2 for v sub x. And for v sub y, we have 3 square root of 2 times the sine. And so we'll have 3 square root of 2 square root of 3 over 2. And I don't want an answer with 2 square roots in it. So here they're multiplied, we get 6. So 3 square root of 6 over 2. And that means I can write the original vector v as three square root of 6 over 2 I plus negative 3 square root of 2 over 2j. So going back and forth between magnitude and direction and component form is just a matter of finding in the one direction, finding the magnitude and the arctan of the angle, and in the other direction, finding the sine and cosine, the x and y projections. Oh, here we go. This is something fun. If a ship travels 25 nautical miles in an hour at a bearing of south 20 degrees west, so south 20 degrees west puts the angle up top because bearings are always with respect to the north-south axis. So we're looking at the third quadrant. We want to find its velocity vector, and we want to write that in component form. So we know the magnitude is 25 nautical miles per hour. And we've got a direction, but we don't have a direction that is in the right notation. So to write this as a vector v, we want the angle to be measured with respect to the positive x-axis. And that means I've got 210 minus 20. So 210 would be all the way from the positive x-axis to 3 pi over 2. So I've got 210 minus 20 degrees is 190. And I want the angle to be in radians. Can we do it in? I actually think that the values will be fine in degrees. So we need also, so we've got a magnitude and an angle. And I want to write, so I want to write V in component form. So I want to find V sub x will be the magnitude of V times the cosine of the angle. V sub y will be the magnitude of V times the sine of the angle. And we know that the magnitude is 25. And let's see, cosine of 190. Okay, so we've got, and okay, I'm in degree mode. So I've got 190. Find the cosine times 25. Get negative 24.6. And then we've got the sine of 190. And it makes sense that they're both negative because we're in the third quadrant, times 25, the magnitude, and we get negative 4.3. So that means that we can write V as negative 24.6, negative 4.3. Or we could write it as negative 24.6 I plus negative 4.3 J. So it really helps to be able to go back and forth between all of these forms. I believe that that is the end of these notes. Yes, so the next is the dot product. And I apologize for not even getting those notes to you. Okay.